All right, good evening. Welcome back to Calculus 2. So we're going to be talking about doing some work problems today. So problem we have today is we have a cylindrical tank with a radius of 3 feet and a height 10 feet, completely filled with water. We are to calculate the work required to pump the water to the top of the tank. It'll be pumped to the top and then out, like this to see if there's a very small lip that just spills out. Okay, so that's what we're trying to do here. Let me draw you a picture of what's going to happen. So here we have cylinder. Okay, and we'll go ahead and draw our cylinder down here. And the idea is that it's completely filled with water. So we're just going to have the water at the very top here. And the idea is we want to take a very small little pancake of the cylinder, like this really tiny little slice of water, and figure out how much work it's going to be to take up this one little piece, figure out that. So if you remember, work is equal to force times distance. And instead of force, what we're going to do is we're going to say that we have the density times the volume. So the units for density is going to be pounds per cubic feet. My volume is going to be cubic feet. This is going to cancel. So we're going to be left with pounds when we're done. So we have to do force times distance. And then we're going to integrate that over the whole piece of container that we're going to be dealing with here. So just to kind of set this up a little bit more, so we're going to say, okay, um, to get our little volume here, okay, each of these little volume pancakes is going to be the same volume. We're not changing radiuses just yet. That'll come. But these volumes are all going to be the same volume. So we're going to say this is pi r squared. And then we have a little dy in here. I'm going to use y's for my little like up and down axis here. So we're going to say, okay, so that's my volume. Okay, so what we're going to do is we're going to go integrating from 0 to what was the height of this whole thing? It was a 10-foot tall cylinder. So I'm going to get the whole cylinder. Okay, we're going to say this is going to be pi r squared. So that's going to be 9 pi dy. That's my volume. Okay, so this piece there is my volume times my density. This is going to be given to you. It's 62.4. I think we're going up here, 62.4 pounds per cubic foot. Okay, so that's my force. And then times distance. And the idea here is that this is going to be 10 minus y for the amount of distance it's going to come up with. So y is going to go from 0 to 10. Okay, so if y is 0, we're not lifting it very much. If y is all the way up here at 10, then we're going to have 10 minus 10. We're not lifting it very far at all. So no work would be happening for this. So my distance here is going to be 10 minus y dy. Let me go ahead and write that a little bit clearer for us so we can see what's going on here. So let's see. We have 9 pi. Here we have 9 minus y. Don't let me forget my little dy because that's part of my volume here. Pi r squared h. Okay. And now we get to go ahead and figure out how to integrate this stuff. So fortunately, with this problem, there's some stuff that will come out. Okay. So right now, right off the bat, I could say, well, I know that we have a 9 and we have a 62.4 sitting here. So we might say 9 times 62.4, just to kind of throw that out of the way. Okay, great, 561.6. So here we have 561.6 pi integrating between 0 and 10. Okay, and I'm sorry, I lied to you. This is not 9 minus y, it's 10 minus y. Okay, because the height is 10 feet. So this is 10 minus y here. I think I wrote that down, and when I erased it, we had that problem. So this here is going to be 10 minus y, because that's the whole height that we're going to be dealing with. Okay, so I've taken care of the 9, the 62.4, the pi. All of those are constants. Those can float outside of the integrals. We have 10 minus y dy. And now we have to integrate this. This isn't too bad. These are the setups are the hardest part of these things. So 561.6 pi. And now we have 10y minus 1/2 y squared, ranging from 0 to 10. Okay, and we'll go ahead and put this together. Okay, I'm going to go ahead and put brackets around this because this 561.6 pi is just going to be waiting for us at the end here. So 561.6 pi. Here we have 10 times 10 minus 1/2 times 10 squared, right? And this is going to be like brackets up here, minus, when I plug zeros in, we all get zeros. Okay, so that's very nice. Usually physical integrals like this, that's how they work. Okay, so here we have 561.6 pi. 10 times 10 is 100 minus half of 100, right? And we're just going to get our 561.6 pi. 100 minus 50, of course, is 50. And we'll just go ahead and calculate this out on the calculator and figure out what our work is going to be. So 561 times 50 equals, we have, what is this, 28,080 pi foot-pounds. So we have foot-pounds, okay? And that would be the amount of work needed for this guy right here. Okay, give me just a moment. I'm going to go ahead and pause us. Okay. Our second problem here. We have an aquarium that is 8 feet long, 3 feet wide, and 2 feet deep. We go visit my Uncle Mickey, my grandmother, her son, Uncle Mickey. He had an aquarium. We'd keep it down in his basement. We were absolutely enthralled by that thing. So we wanted to sleep in the basement, but that didn't matter because we could watch the fishing all night, and that was just fine with us. So what we're going to do is we're going to draw a little picture here. So we have this, pretty much this box, okay? So pretend this is a good picture of a box. I know it isn't, but that's okay. So, and what we're going to do is we're going to think about the same kind of thought that we had for the last problem, okay? Where again, we want a force times distance is equal to my work, okay? So for our force, we're going to say that that's going to be my rho times my volume. Okay, my density times my volume. That's going to give me, right, pounds per cubic foot times volume of cubic feet, and that'll be pounds. Okay, and then times the distance that we're going to make this water travel. So we're going to take each of these little flat pans of water and push them up to the top. Okay, so here we go. We're going to have an integral going from, what is my depth here? We have, it's this 3 over here. This is 8 feet long, okay? 3 feet wide, and we said this is 2 feet deep, okay? So we're going to go from 0 to 2, okay? So we're going to push all of this water out, okay? We're going to have our density, so it's 62.4, okay? Pounds per cubic foot, pounds per cubic foot. Okay, times length times width. So we have 3 times 8. And then my height is going to be a dy. Okay, so this is the volume idea that I have here. Okay, and now we have to multiply it by a distance, and that distance is going to be 2 minus y as we go through this thing. Okay, so that's what we're trying to figure out now. So we're going to integrate this piece here. So let's go ahead. Again, we have a couple of things that we could deal with. So we're going to say this is 24, 3 times 8, times our 62.4 integral from 0 to 2. We've taken care of the 24. We've taken care of the 62.4. And we have a 2 minus y dy. And that's what we're going to go ahead and integrate. Okay, so off to the side here, I'm going to go ahead and get my little piece here. So do I have a calculator anywhere? I have no idea if I do or not. Hold on for a second. Pause here for a moment. Okay, so here we go. That's right. I was going to multiply this out for us. Okay, so we have 24 times, where are we here? We have 62.4. So we have 1497.6. Okay, we have 1497.6. Integral from 0 to 2 minus y dy. All right, so we go ahead and calculate this integral. So we have 1497.6. Here we have a 2y minus 1/2 y squared, ranging from 0 to 2. So let's go ahead and plug this in. So we have our 1497.6. Here we go. We have 2 times 2 minus 1/2 times 2 squared minus the 0. So this was the upper limit and this is the lower limit. Okay, so we'll go ahead and deal with that. So here we have 1497.6. Here we have 4 minus half of 4, so 4 minus 2 is equal to 1497.6 times 2. And we'll go ahead and calculate this off here. So 1497.6 times 2 equals, and there we go. We have 2995.6 foot-pounds of work here. So those are pretty nice. Those are pretty easy. If you had to warm up on one, this is the kind of problem I would suggest warming up on, because it's volume times density, and then just integrate over the volume of water that you're going to be dealing with. Okay. Again, let me pause this for a moment. I'll be right back. Yeah, our third problem here. We have an inverted conical tank, height of 12 feet, radius of 4 feet. Don't ask me how this stands up. Maybe there's like an extra stand or something that we've got sitting here, but we've got this giant like sort of ice cream cone. And for whatever reason, instead of having this drain out, we are going to push the water out of the cone this way. Okay, so we're going to push the water up and over the top of this thing. Okay. So we know that this piece here is 4 feet. It has a radius. And we know that this whole piece here is 12. Okay. So unlike in the last problems, we have a variable radius. Okay. This is changing radius as it goes up. So we can't just, like if I pick a little slice here, it's not going to quite work because the slice here is going to be a little bit different. My dy is going to be a little bit different depending on where I am. Okay. So we have to worry about that. So what I'm going to do is say, well, this here is a line, okay? So I know if I go ahead and draw my coordinate axis here, if I'm going to draw it like this would be the origin. So I would have a line going through the origin. So we have some kind of a y equals mx as far as equations go. Okay, remember what m is, and this rise over 1. So we have to say, okay, well, how much does this thing rise? And it rises 12 feet. And what's the run? And that's 4 feet. So we have y is equal to 12 over 4x. We figure that out. So we have y is equal to 3x, or we have x equals y over 3. Okay, so that's what we have so far. All right. Now, just like we did in the last section, like I've got this y over 3 as a radius. And what I'm going to do is I'm going to spin this thing around this axis in order to get the volume of this piece. Okay, it's like amazing if we had ever like rotated a line or a shape around an axis before. I wonder if we've ever done that. So what we're going to do is, again, we're going to set up our work integral. So work equals, we're going to say force times distance. Okay, and again, our force is going to be rho times our volume. Okay, and then times our distance. We're putting all this water out there. Okay, so the distance is this time the twist is going to be 12 minus y. That's my distance for this plane. The density doesn't change. That's going to stay at 62.4. Okay, and then to get this value here, we have to rotate this thing around. Do you remember how to do that? That was, actually, let me go ahead and erase that integral. That was going to be the integral. We're going to go from 0 to 12. That was going to be pi r squared, and my r is going to be y over 3 squared. Remember, we're rotating, getting volumes of solids of revolution. This is exactly what we're doing. Okay, so I have our y over 3 squared, 12 minus y, and then we have to go ahead and simplify this out a little bit. So we're going to say this is going to be 62.4 pi 2 squared, 3 squared is going to be 9. So we can go ahead and drop that there. I put the pi in front of the integral sign, so that's going to be out. So we can say that's going to be 0 to 12. And here we have our y squared from this piece here times 12 minus y dy, right? Because we have our little volume shape here, right? So we have our pi r squared effectively times our dv, times our dy rather. Okay, so we can go ahead and deal with this. So we've got 62.4 pi over 9, 0 to 12. I'm just going to go through and multiply this out. So we've got 12y squared minus y cubed dy, and then we're just going to deal with some calculus here. This isn't too bad. Okay, so we've got our 62.4 pi all over 9. Here we go. We have 12y cubed over 3 minus 1/4 y to the 4th, going from 0 to 12. Right? Not too bad. Put this in here again. So we'll go ahead and plug in 12s in here. So we have 62.4 pi over 9. Here we have, this is a fancy way to write 4. So this is 4. And then we're going to say this is 12 cubed minus 1/4, 12 to the 4th power. Okay, and be able to do it that way. Okay, minus, when I plug in 0, we're just going to get a bunch of zeros. Okay, so we're going to be able to say something like that. Okay, so now we can go ahead and plug this into our calculators a little bit. So we have, go ahead and turn you on. So we've got here, we've got 4 times 12 cubed, right? Equals minus 0.25, that's 1/4, times 12 raised to the 4th power. Okay, and that'll take care of all the things I have to do that. So that's going to be 1728. That's this piece in here times 62.4 all over 9. Let's go ahead. Oh, and there's a pi sitting here. So let's leave the pi out there. Because usually these answers are usually given to you. Pi is usually just sitting nicely at the end here. Okay, so we'll say we have 62.4 divided by, we'll say times 17228. And then we'll say divided by 9. So that'll take care of all of those things there. Okay, enter. And then we have 11980 pi foot-pounds. Okay, and that would be a good answer for us. 11980.8. If we had to multiply this thing by pi and just get the whole general thing, we could just multiply it by pi times second function pi equals, and then there we would have it. We have 37,638.79 foot-pounds. So approximately. Okay, and then go ahead and look at that. What do I just have here? 37,638. 638 points, and it would tell you like how many decimal places to put your values to, but we'll say 3 for this one, 0.793. Okay, but if they asked you for like a decimal approximation, they would definitely tell you, like, give me to 2 decimals, give me to 3 decimals, whatever it is. Okay, but that's how you do a problem like that. I think 3 problems is probably good for this video. So I'll do a couple more in a little bit, but that is the general idea of how you're supposed to work on, how you're supposed to calculate work problems. Okay, thank you very much for watching the video, and I'll see you in the next one. Take care.